the third event of Share It. And I want to start with a small PowerPoint to show you some things. So these are the posters of our first 3 events for those who have not been here before. I would like to talk about briefly how to get to our channel, YouTube channel, where these events are uploaded. So anyways, you write SQ Malta and YouTube, and this comes up, and there are the channel, the tutorials, which for now we have only one about 3 of operator, which could help you and then there are the videos. Something else, since we are in the second semester, I would like to remind you that on our website there is a section about for second-hand books, so you could check for books or sell yours if you don't want them anymore. So that's it. So we can start. Our talks for today are going to be quantum mechanics. Kris Bajada will be talking about that. How to cook meat. Hili will be talking about that. And this is quite a long name for Interpolation of subjects by Fabian Micallef. So I think you will have to start.
The first thing you have to know is what actually is meat. Meat is basically just muscle that has been aged slightly in its own juices. These juices are basically the toxic substances, that are produced after the organism has died. The respiration still is going on, anaerobic respiration goes on, lactic acid is produced. This lactic acid activates enzymes, the enzymes break down filaments, and thus the meat becomes more tender, much more manageable to cook and eventually eat. Good meats you will notice immediately because it's softer, it's easier to cook, it's easier to handle. Badly preserved meat is tougher, when you cook it's much more difficult to chew, it doesn't cook properly, and you have all these problems after all. What happens is that you have the meat, if you age it too much however, then you will eventually end up with a dried husk, which is dried meat, that's jerky, that's the process of preparing the meat. What happens when you cook meat is you have the protein. It's compact, it's been made through part of muscle which is made to withstand loads of stress, to be stretched, to be pulled. When you cook it, this denatures, this breaks down. Why does it release all the juice, those juices? Those juices are the water. Each cell is packed with water, even though after you've prepared it, after you've aged it, after it's been broken down slightly by the enzymes, you have that water that's still in there inside the cell that's not broken up yet. When you cook it, the proteins denature and that water just rushes out. When it rushes out, the meat actually shrinks. If it shrinks, it actually means you have a really nice piece of meat there. Otherwise, if it doesn't shrink, it's usually either gone off or it's not been aged properly, or it's just heavily processed. So, there are 2 types of meat that I'm talking about today. I'm omitting fish because that's much more complex and would have taken a longer time to explain. I'm talking about red and white meat. Red meat is my favorite. It's much more tasty, it's much more red, it has much more intense flavor. It's a bit more unhealthy because of all the ammonium compounds in it. Basically, what red meat has more is it's packed with myoglobin. Why? It's slow-twitch muscles. It's usually taken from parts of the muscle that contracts slowly over time, the muscle that helps to keep posture, to hold you upright, for example, the back muscles, some of the leg muscles. You have both kinds of twitch muscles in the same muscle fiber. You have slow and fast twitch. However, in red meat, fast twitch predominates. This happens because you need myoglobin to sustain long periods of stretching, and this when you have fast twitch muscles needing energy, the hemoglobin takes most oxygen to it and reduces the amount of oxygen to the myoglobin-rich muscle. So the oxygen comes from the myoglobin and allows the muscle to be stretched. An interesting fact, when you're cooking it, myoglobin changes with temperature. This is protein. It denatures as the more you heat it up. Around 60 you have the red myoglobin color is still there. It's edible, the meat is edible, and that's the rare. You can easily test if it's rare, it's good for eating. You can put your fingers like this and just touch this piece of muscle here. It is actually quite soft when you do this. When you do this, that's medium. It's much thicker, much more tough, but it's still, you can still feel it's soft on the inside. If you do this, that's the well done. If you cook it more than that, that's burnt, basically. The marbling in it, we'll get on further on. If you have a bit of fat content in it, it's actually a hallmark of a good cut of meat. White meat, on the other hand, is, as we said, fast, rich muscle. White meat is leaner, it's easier to cook, it cooks much faster. It basically is less dense than red meat, and it's, as again, people say it's healthier because it doesn't have as much myoglobin in it, which myoglobin, when cooked, eventually break down to lots of ammonium compounds, which are difficult for the liver to break down. White meat has another property. When it's cooked, the protein denatures. However, the protein molecules that are denatured eventually will coagulate together, creating that white color. This can be easily seen in pork, chicken, and rabbit meat. All three are very white meats. They're very nice, quite lean. They're very much used in diets if you're interested. So, back to the fat content. Fat is important. You need fat in your meat. Why? Simple. Most of the aromas, most of the flavors, most of the meaty taste is organic, organic compounds. Fat is an oil, it is an organic compound. Thus, the most important flavors are stored in the fat, not in the water that's stored inside the muscle itself. When you cook it, most of that fat eventually disappears. It melts. It releases all those flavors inside the meat. It makes the meat tasty. It's the reason why meat tastes like meat, basically. Well, it's my favorite kind of meat. As you can see, I'm actually quite fanatic about food. Then you have the white meat. The white meat is actually very, very, very lean. It is the reason why it tastes so light. It tastes a distinctive taste. Pork, people think it's actually quite a fatty meat. It's actually very lean, very, very lean. The only pieces of fat in pork are in bacon, and the largest fat content after that is on a small bit you see around the pork chop. That's the most you can find. Other parts of the pork, there isn't as much fat, just very slightly. It's just basically around that, and the organs, obviously around the organs from the flesh. That's something else. Marination.
Can I ask a question? What fat content? For white meat, does white meat have fat content? Because when you eat it, usually
the fat is placed in specific positions. It's not spaced throughout the meat, as you saw. See, so the red meat, you have the marbling. That's called marbling, by the way. Sorry. That's called marbling. That's the reason why you have even distribution of the fat. And eventually, when you cook it, that even distribution gives the even distribution of the taste. In white meat, you have the fat in the corners. That's where the fat is. It doesn't go through the muscle fibers. It goes on the outside. It's the reason, for example, why you have, have you ever seen ham being prepared? All the fat is on the outside. It doesn't go there, it's there from the start.
In chicken, for example, where is it placed? Because I've never heard that. Well,
have you ever cut open a whole chicken?
No.
Then that's why you don't know it. The fat is distributed evenly on the inside, in certain areas, or in the wings, for example, or in the skin itself. The skin itself in the chicken, the taste difference. Yes, exactly. The tastier it is, it's probably packed with fat. Because the fat, again, keeps the content taste. Marination again. Marination is important. Why? Simple. You have three components of every good marination. You have the acids, the oils, and the herbs. The acids are, as you can say, the denaturing component of the marination. It breaks down the meat. It makes, as I read and quote, tunnels inside the meat. For the oil to carry the aromas of the herbs inside. It evenly distributes even more. If you don't have a very good marbling, for example, you can use marinations to distribute a good taste, a nice taste throughout the meat. The herbs used also, usually if you just cover it with herbs on the outside, you get that herby taste on the outside. it can be quite sickly. But if you do it this way, the herbs go on the inside of the meat and it's evenly distributed. It's really, it makes it so much different from the normal meat in itself. The reason why meat tastes like meat, the Millard's reaction or the Browning reaction, as it's normally known by chefs. This is basically the amino acids and salt. They react together at intense temperatures. Then they give that brown color. That brown color is the reason why it emits that nice meaty smell when you cook it. It allows for a cover to be created around the meat, and it gives that meaty taste. So you have that dry meaty taste on the outside, and you have the juicy red coloration on the inside if you cook it medium or rare. Some people like it well done. Again, that's completely another topic. But you have these two contrasts, and when you cook it, the myoglobiin on the inside doesn't get the nature as much as on the outside, and you have all these aromas, all these tastes coming in your mouth. The juices help in distributing the flavor of the browning reaction on your taste buds. If you have a very dry piece of meat, it doesn't taste as well. So usually the dry meat, dry cooking, they use gravy. The gravy helps in the distribution of the taste around your mouth. And finally, cooking. For this reason, I only used grill cooking. You can use barbecue or whatever. It doesn't really make a difference if it's charcoal, wood, or gas, unless you're a very professional taster. You know different tastes, different aromas of smoke. Smoke doesn't give taste to the meat. It adds to the taste, doesn't make the taste better. What happens is the flame, this here, by the way, gives the choice of two types of cooking, the direct and indirect heat. The direct heat, you put it over the flame, you see it brown up on the outside, you have the nice juiciness on the inside, as we said before. But the indirect method is you roast it on the outside, you make a nice crust so the juices stay inside, and then you put it on the side at lower temperature and leave it cooking there. So you have an even cooking throughout. This is where you use the gravy to distribute taste even further. And finally, you eat it and enjoy it. Thank you for listening. This wasn't very scientific.
Quantum mechanics. The laws here seem completely different to the familiar laws that govern our everyday ways. For example, certain things that we think are impossible are actually possible in the quantum way. For example, I can't go through a wall, I can't walk through a wall, but there's a theory that subatomic particles actually can go through a wall. They sort of borrow energy from the future and they'll eventually give it back. It's still a hypothesis, but it's not never been actually proven. It is the most fundamental description of matter we currently possess. The laws of quantum mechanics rule over every atom and tiny particle in every piece of matter, in stars and planets, in rocks and buildings, and in you and me. In the quantum world, particles don't like being tied down to just one location or follow just one path. For example, they can go two paths at the same time. An example of this is the double slit experiment. Although this might sound strange, we have been using these strange laws to make predictions how atoms and particles should behave, and after experiments, proven correct. Until the 20th century, it was thought that the motion of atomic substances and particles could be explained with normal Newtonian physics. But then they found out that they couldn't really explain with it. For example, Galileo's laws and Newton's laws break down when you use subatomic particles which travel at the speed of light. How do the laws start? Scientists try to explain some unusual properties of light. For example, the kind of light that glowed from gases when they were heated in glass tubes. When scientists saw this light represented, they saw distinct lines of distinct colors and no stream of color you see when you look at a normal prism. For example, we've all done this when we were young. In our O-level physics, we get a prism and we look at light. We see like a rainbow of colors. But in quantum mechanics, we see a sharp shade of grey, a shade of blue, a shade of green. There's no stream, there's just distinct colors. According to Maxwell's equation, the Maxwell's laws of electricity and magnetism, an electron which is negatively charged would fall towards the nucleus because of the attractive force of the positively charged protons located in the nucleus, and thus atoms could not exist. However, we know it's not true because atoms don't exist. He thought that atoms resemble tiny solar systems with a nucleus in the middle and electrons orbiting around it. But the difference is that, unlike planets, they had fixed orbits. They could not travel through the space between them. It's as if, for example, Mars just shifting through its orbit without traveling through the space between it. A lecturer once told me, and he gave me this example, it's like the Holy Spirit. It's there and it's there. It's not anywhere away. Actually, it was Professor Greenman who told me. Wow. What causes the delay? When an electron in an atom, when it doesn't do an atomic cycle, the electron becomes agitated and moves from one fixed orbit to another. This is known as a quantum leap. Each downward leap emits energy or radiation in the form of light at very specific wavelengths, and that's why atoms produce very specific colors. You might ask yourself, why doesn't it release energy when it goes up, not only when it goes down? For example, I got them over here. I'm getting it up, there's no heat emitted, there's no sound. But then when I look at it, it releases heat, it releases sound. And that's why when electrons go down, they release energy. So basically, easy to write. This is how we can calculate the energy. What do we see from this equation? E is equal to h mu lambda. This shows that the greater the energy, the lower the wavelength. For example, a transition from here might produce one type of wave, while this might produce another wave. For example, you can see from the equation in the previous slide, you see that the energy is inversely proportional to the frequency. The quantum leap. In the quantum leap, electrons go direct from one fixed orbit to another. We see them without traveling through the space between them. It just goes from here to here without traveling through the space between them. This is because energy comes in discrete chunks called quanta. The fact that electrons cannot exist between defined quantities explains why electrons do not spiral into the nucleus. It can jump from one orbit to another, but it cannot exist in it can't exist in the space between. For example, imagine it's on the lowest orbit. It can't fall down because it can't travel through the space between it. So, although there's an attractive force, it can't. Because electrons can't travel through the space between them. There are currently experiments that prove some things of quantum theory. One shows that the quantum theory that basically it shows that we all know that it's like this. It's not like this, and like this, and like that. But this experiment proved it in quantum theory for quantum particles. The second one explains it. The electromagnetic radiation or light. We all know light is a wave, but this experiment shows that they can also act as a particle. And that particles can also act like waves. Atomic and molecular spectrum. For example, we see that there are spikes, they're not a gradual thing. And that shows how it's just that and that. From this we can conclude that the energy from an atom normal or molecule is confined to discrete values. Energy can be discarded or absorbed in only packets of energy, known as quanta, as the atom or molecule jumps between its allowed states. The frequency of the radiation is related to the energy difference between the initial and final state. And there's the photoelectric effect. Basically, this experiment shows that light can also act as a particle. Basically, what happens is that photon, before the photoelectric effect, we always thought that light was a wave. But the photoelectric effect showed that if you shine light on a metal, because it has a specific frequency, it will eject electrons. And that showed that, for example, if it's, like for example, a car, hitting another car, it will eject something. And for example, the photons are hitting electrons on the metal the same way, just like that when we move another car if it's hit. No electrons are ejected regardless of the intensity or of the radiation, unless the frequency exceeds the threshold value, characteristic of the metal. For example, we saw in the other experiment, in the first experiment. The kinetic energy of the ejected electrons varies linearly with the frequency of the incident radiation, but is independent of the intensity. Even at low intensities, electrons are ejected immediately if the frequency is above the threshold value. Basically, the bottom paragraph turns out like this. Basically, what that symbol means is that if it doesn't have enough energy, no electrons will be ejected. Then there's the electron diffraction. Electrons are the waves. In this experiment, the beam of electrons was directed on a single crystal orbital, and the expected electrons show the variation in intensity with angles that corresponded to the pattern that would be expected if the electrons had a wave character and waves diffracted by the layers of the atoms in the solid. Here's another interesting thing about that. They found out that if you look, recently they got an electron, they did this experiment, and they got an electron band, and they shoot electrons. If the scientists didn't look, it would show a wave pattern. If they did look, it would show as if it was a particle. The reason they thought was because, for example, how do I see the world? Because light is hitting you and coming back into my eyes. It's not affecting you that much. But if we think on a molecular level or atomic level, a photon is quite similar in size to an electron, so it will hit it and cause a change. So then they come up with a theory, because they found out that light can act as a particle and particles can act as waves. So then came the group and came up with a solution to make call it an afterwave. This is to show the probability where the electron is. And what dimension. Then that's in 3 dimensions. The results from this equation show us the probability of finding an electron in the space surrounding the nucleus. For this equation, there are only some distinct solutions, which means that electrons are only present at some distinct energies. In other words, electrons are only present at some distinct levels or shapes. However, this equation can only be solved up to a certain level of accuracy, only for speeds containing one electron. And one electron, like we see in a hydrogen atom. In a system where there are more than one electron, when there is more than one electron, it comes to an accurate. Then there's the Heisenberg uncertainty constant. Heisenberg postulated that the exact measurement and determination of the properties of a particle cannot be achieved simultaneously. The two properties in determining the exact position are the area and space the particle is located and momentum. However, these two depend on each other, and if one is measured, it introduces an uncertainty in the measurement of the other property. This introduces the concept of the probability. The polar coordinate system is a coordinate system in which each point on a plane is determined by a distance from a fixed point or radial component, or an angular from a fixed direction. By using the wave function, we can determine the probability where an electron is most likely to be found. Rather than a single point, it is in a each wave function has a different shape, and a different spatial distribution, and also different distances from the nucleus. These are examples. You can see like the different shapes of the top particles. Every electron moves independently of it on its own in a field created by the nucleus and other electrons. It is called the orbital approximation, which is defined by the product or quantum numbers. Any electron around the nucleus has a very specific properties, which determine its total energy, divided into 4 different forms, and each of these reflect an energy level, and each is given a quantum number. And no two electrons in a single atom have the same quantum number. There is a principal quantum number, there is the orbital quantum number, the magnetic quantum number, and the discrete quantum number. The principal describes the distance from the nucleus. The orbital describes the orbital motion of the electron around the nucleus. The magnetic quantum number describes the electron's field, the magnetic field between 1 or +1. And the spin quantum number describes the electron still on its own axis. Basically, it can be clockwise or anti-clockwise. Method of relation. According to Bohr, measurements change integrity. We believe that before you measure or observe a particle, its characteristics were uncertain. For example, an electron in the double-slit experiment before the detector that pinpoints its location, it could be almost anywhere in the whole range of possibilities until the moment you observe it. And only after that moment, the location uncertainties disappear. For example, a wave you can never be sure where it is. But then, once you look at it, like I described before, it chooses one place and then it remains all the other possibilities. However, Einstein believed in certainty, not only when something is measured or looked at, but all the time. What does he mean by this? For example, he once said, I like to think that the moon is behind me, even when I don't look at it. Quantum entanglement. It is the craziest prediction that comes from quantum mechanics. Basically, it means that if you get two electrons close enough to each other, they will become entangled. And once they're entangled, they share properties. And no matter how much you separate them, they, for example, if I look at one, it automatically affects the other one. Let me give you an example. For example, I entangle two particles and I separate them by infinite distance. If I look at one particle on it and I see it has its spin is clockwise, I can say with certainty that the one light years away is anti-clockwise. That's what quantum entanglement tells us. And the experiments have shown that it is actually true. Application of quantum mechanics. Quantum computers, using the principle of quantum entanglement. Nowadays computers use the 1 and 0 system, but with quantum mechanics we can use entanglements, and it will allow far more calculations. For example, a computer can do many calculations at the same time. Exactly. It will basically our computing capabilities will increase infinitely. And that's an example of a quantum computer. It's still in its infancy. For example, in the 1950s, a laptop like this was out of this world. A computer in the 1950s was as big as this room. For like quantum computers nowadays, we expect that in maybe 100 years it will be with not smaller. Or the teleportation, using the principles again of quantum entanglement. Victims such as the transport link or death chamber. It's called death chamber because, for example, I want to have a 15-minute break from my lecture one day, and I want to go to France. Or on Bajada, we've been quite nice. If sometimes we go to France, we go to Germany, we can even go to Mars. With quantum entanglement, this is possible, but there's just one problem. We call him a victim because in this process it will see all the molecular bonds that there are, but then it will copy it, you will be literally destroyed, and you're definitely going to live out your life. There's still some ethical issues about this. Think about it. Then the question is like, what is the soul and things like that? Is the soul just a combination of atoms or is it something deeper? If you want to do it, I guess the laws of physics allow it, mathematically it's possible, but at the end of the day it's up to you, and you will be just, not even dust, you'll just be some protons and neutrons and electrons at the bottom of the chamber. It will be that way exactly, but it's not here. It's not your atoms.
My presentation is about interpolation of images by transformations, which is a sort of a complicated way of saying we're mixing pictures using matrices. And I assure you that is the only complicated thing. I've made the point that I use no mathematical ideas that are beyond intermediate, and they are not in A level just because they don't bother to present the construct. So they don't bother to tell us what a vector is and what a matrix is. But apart from that, there is nothing which is harder than an intermediate. So, and of course, people that have intermediate physics, even they know of these constructs. Maybe not the way to use them, but the idea of the construct is there. So, we're going to interpole images, we're going to mix images, and to mix images we need the images. So, meet the parents, so my mother is my dad, and then I'm going to mix these pictures. I'm going to mix these pictures and create an average. I create this average by not only when it comes to the color, because that would be simple and would really involve, and it wouldn't really involve anything beyond simple computing, but also in the shapes. So the average will be with respect to the shape of the object and the color of the object. So the necessary, well, first, this is just an example. You can use any two pictures. What I am doing here is this presentation is just a package, but the idea of it is that mathematics really is just simple logic. Well, mathematics can look complicated, but really at the end of the day, it's just a logic game. It's like chess, but that is the main point. The second very important point is that those topics which were presented to us as something separate, something discrete when we were in O-level, they're really just interlinked, and we will see this. And yes, of course, really, you can do something which is interesting without using any complex mathematics. So, first thing is we need to decide what are the important points, the nodes of the two images. And of course, there needs to be a relationship between the points. So each point in the first image needs an equivalent point in the second image. We call it a bijective relationship. Using these points, we subdivide the picture into triangles. Triangles are the most simple shape in which you can divide an object. And we have a number of theorems which we learn at A level, which can easily be derived from what we learn at O level, which in such a way that we can relate the triangles to each other. Note that since the points were related one to one, so equivalent one for each one, there's an equivalent triangle for each other triangle in each image. So for now, we're going to forget the pictures, and we're just going to concentrate on a given particular triangle. Essentially, all this is for the benefit of who has mathematics. Essentially, what is happening here is that we have a transformation which is a matrix. A matrix is just an array of values. Fortunately, it's not a computer-generated reality, which makes us think that we are safe while we are being used by the computers. And this such a transformation just modifies vectors. They will have two-dimensional vectors on the plane, so we call y1 and x1. So just modified, and of course, for each pair of triangles, you have this transformation. Of course, this is just the derivation of the matrix used. It's quite lengthy, but it's simple. It's just computational. The idea itself is quite simple. It uses basic matrix theory. So we've just taken one matrix on the other side, and we just combine the matrices, and we get the result down there. Now, the point is of the exercise is to create an image which is what we call a weighted average. So an average which is not direct, it's not exactly in the middle, but an average which, using a parameter, this parameter I call it little t, choose it from 0 to 1, and according to what value I put with this parameter, I modify the average and say, so if t is 0.1, it's closer to the first image. If t is 0.9, it's closer to the second image. If t is 0, it's the first image, and t is 1, the second image. And that is just the transformation. So transformation t takes me from the first image to the second image, and t dash, which is a weighted average again of the transformation. So we have t times the first, t times the transformation from first image to second image, and to balance it out, 1 minus t of the effect, so that we can get the weight average. And with the second transformation, so we've got t dash, the transformation from the interpolated image to the first image, and the double dash from the interpolated image to the second image. You can see it's just t, it's just t dash, t. So just first you apply, you go back, and then you go forward. We need this so that when we create the interpolated image, we can go from the interpolated image to each images, and then take the information from those images to form our image. So that they take a pixel, consider a pixel in the interpolated image, we see when it gets plotted in the first image, in the second image, and then we can just take from there an average. It's just that. Now, this part is more relevant to the fact that we have a picture and we have many triangles in our picture. So we need to see which pixels are in which triangle. And to do that, we use this simple formula, which can be easily derived using O-level graph theory, essentially. And so I can say that we're using vectors, we're using matrices, and now we're introducing the concept of graphs. So 3 completely different topics, which no level are presented. It's totally different things, but they are now closely linked, and this pattern is you can see it across all of mathematics, because at the end of the day, the logic is the only thing that there really is. So, using this formula, you find the distance of a point from a line with the sign plus or minus being plus if it's on one side and minus if it's on the other side. And then at the end of the day, that is what we are going to use. So here we see, if a point is contained in our triangle, it is on the same side for each of the 3 lines. If, like point A, point B is on the same side for 2, so for x and for z, but not for y. So the things we have just take the sign from our calculation, and we say if they are all negative or all positive, it's fine because you are in there. And if one of them varies, then you are outside. So the point is not included. And then at the end of the day, this is just a transformation where you take the location, where you find the location for the first matrix and the second matrix using the values for the particular pixel we've chosen in the interpolated image. So you've got our pixel, which we know now where it is, in a given triangle. For that given triangle, we know the transformation, which takes us to the first image and to the second image. So now we can see which pixel is the equivalent pixel for that image, for the first image, and for the second image. And now that we know that for that location, modified in such a way to go with the first image and the second image, we can just take the color, and the color is again every image of the colors we can find in the 2 images. So now we just have RGB, that is just a vector of 3 values, which can go from 0 to 255. And of course, you can take an average of that, average for the red, average for the green, average for the blue. You just, at the end of the day, put them together and form your color. Now, these are the results. I have created this image using a computer program, and I did it from 0.1, from 0 to 1 in steps of 0.1, so that you can see the progression as the average moves from one image to the other image. Now, of course, this assignment, this project wasn't only related to mathematical ideas, but it also had to be computed, software to be developed to create these results, and of course, to compute this mathematical process, no complex ideas are used. You just use matrices, these array of numbers, and with these array of numbers, you can really present any amount of data, of course, to the limitations of your hardware, your computer. You can increase the number of nodes, for example, and you will have a more accurate image, but of course you need more computational power. And these images, they are 300 by 400, and I have a respectable laptop, but to generate each image, it took the computer over 2 hours to generate each image. So you can imagine how much work it involves if you're using a larger image or a large number of nodes. And now I just want to see how the image progresses from an image which is purely 100% the image of my father to an image which is 100% purely the image of my mother. And no, in the middle there isn't a freak point where there's someone that looks like me. the true average. This is like a translucence. And now, what I wanted to add to this is that this essentially is the basis for computer-generated movies, images, whatever. But this is the basic concept. You can take what I've done here, and you can extrapolate, imagine the value of t, instead of being limited to between 0 and 1. It could be done 2, 3. You just extrapolate the features, you exaggerate the features, and you can, of course, well, in this case doesn't make much sense, but say you've got an image of maybe the growth of a plant, and you've got an image where the plant is 5 weeks old, and an image where the plant is 2 weeks old. You can extrapolate the same idea to have a simulation of what the plant will look like when it's 7, 8, 9, 10 weeks old. Of course, again, this is the basis for your computer-generated movies. It's just in 3D instead of 2D. And at the end of the day, it all boils down to two-dimensional vectors and three-dimensional matrices. Just rules applied, and those rules simulate the shapes of the character. You've got, let's say, some vectors are constant, the bones, the general structure. Then you just flesh that out, and you modify that accordingly to what you want. So you've got simple mathematical operations, simple mathematical ideas, which I'm sure you've understood. No need to be a PhD in maths. And with it, you can create something which is interesting and something which we can touch with our hands, something which is up there. So, thank you.